Good evening, everyone. Thank you for coming. My name is Bruno Faria, and I'm EMR Solutions Architect with AWS. And today I have with me Ritesh, and he's a Senior Product Manager at Vanguard. And for our session today, we're going to be talking about migrating big data applications to AWS. So part of our agenda here today, we're going to deconstruct some of the on-premise environment and also check out some of the challenges that on-premise solutions might have. Then we're going to talk about migrating each individual component into Amazon EMR, as well as other AWS analytics services. And then last off, Ritesh will be finishing off and telling us how Vanguard performed their migration over to AWS Amazon EMR. Now, I'm going to run through this a bit quick, so I would like maybe to leave a few minutes for you guys to have any questions that you may want to ask. So if you can bear with me, and I'm going to run through this, and hopefully we can cover everything here today. So we're going to start off with deconstructing the on-premise environment. And let's take a look, for example, of a cluster of a 1U server that has maybe 32 to 64 gigabytes of memory, 6 to 9 terabytes of hard drive, as well as 12 cores. A server with those specs might usually run for $3,000 to $4,000. And that's also not accounting for your network switches, your racks that you have to purchase, and also the open source Hadoop distribution or a commercial one if you're using that. And also one of the big factors that we have here is the storage. Take something like HDFS, which by default, a typical configuration is 3 times the replication factor. And for that, you need 3 times the amount of storage needed. Also, we usually typically see an on-premise environment where every single workload type actually runs on the same cluster. So take your large-scale ETL, your machine learning, your NoSQL data warehouse. You see all of these workloads and applications all operating within the same cluster, which this leads us to this situation we see here. Well, here we have a swim lane of jobs, and if we refer here to the left side, there are 5 different analytics applications or workload types. We can see up in the top particular hours in the day. So if we take over here the beginning portion of the day, for a few hours there, the cluster is overutilized, where you have every single one of those workloads running at the same time. Now, at other times in the day, there's only 2 workloads running, which that makes it for an underutilized cluster. So here it leads to this overutilized at peak hours and underutilized situation for the cluster. For an on-premise solution, there's also the role of the big data administrator. Take, for example, that big data or Hadoop admin. They need to be able to get hardware, be able to replace hard drive, backing up the solution, taking care of disaster recovery, amongst tuning jobs, configuration management, and many other things. So this, you need an entire team to be able to dedicate their work hours for that. So let's talk about some of the challenges, some of the main challenges that you have with this on-prem or a managed environment. One of the things is a tightly coupled compute and memory storage, a tight coupled storage with your compute resources. So that means that usually if you need to scale simply based to accommodate more storage for your cluster, let's say you need more HDFS, you're going to lead into a situation where your compute and memory resources are underutilized. So this, also taking back to the swim lane of jobs that we saw earlier, can be a cluster that's overutilized at peak hours and underutilized at other times in the day. The end result here is that it is high cost and low efficiency. Also, system management difficulties with an on-prem or a managed environment. You need to be able to have durable and disaster recovery, durable storage and disaster recovery for it. And part of that is actually a lot of work, especially as your data grows. So when you're talking about terabytes or even petabytes of data, we all know that it's not going to be easy for you to be able to keep that as a durable storage or as well as managing disaster recovery solutions for it. Also managing the distributed applications, which is also not an easy task itself, and managing multiple environments like your Q&A, your dev and test environments. All of these are things that adds on to the complexity of being able to manage this environment yourself, and which requires you to have an entire team dedicated for that. So let's talk about now migrating these components into AWS or migrating these workloads. Some of the key migration technologies, some of the key migration considerations we have here. The first one that we're going to be talking about is to do not lift and shift. And what we mean by that is many times a customer might look at a migration as simply, well, let me provision a equivalent cluster of EC2 instances where it has the same amount of disk space, same amount of memory, as well as same CPU, and that's going to be it. And then I simply need to lift and shift that over, and I'm done. Well, it's not usually the case. So if you're migrating to a technology such as Amazon EMR or other analytic services within AWS, you should not lift and shift. Instead, you should deconstruct your workloads and use the right tool for the job. We all know there's a vast amount of applications in the big data realm, and these applications can do many things, but there's usually one particular application that does something better than others, which we'll talk about later on. And next, which is going to be a primary focus here on this session today, is about decoupling your compute and your storage with Amazon S3. So Amazon S3 is pretty much the bread and butter for many of the analytics services as a backing store for it. And we're going to be talking about how you should be decoupling that storage for building an application or a design that's actually low cost and scalable. First thing, let's deconstruct workloads and take a look at some of the different analytic types and frameworks. Now, there's actually a vast amount or a large amount of different workload types. But what I can fit in the slides, I kind of put on the core ones that we'll talk about here today. So first we have an example of a batch workload, which that might include a daily or weekly reporting tool, and that might take minutes or hours to run. You also have your interactive workload, which might include something like using Spark, or an example of using for that is a service dashboard. And again, it takes minutes to run, and it could use something like Redshift, Amazon Athena, as well as Presto and Spark for it. Next, we also have stream workload types, which takes milliseconds to seconds to run, and those usually might include your Spark streaming application, or Flink, Amazon Kinesis Analytics, and so on. And one of the newest one that I decided to add here is also your AI or artificial intelligence workloads, which may take milliseconds and minutes to run, and that includes something maybe like fraud detection, or some kind of prediction, text-to-speech, and so on. So we're not going to touch too much on that, but I just felt like you should also list, as it's been a pretty hot topic lately, is about machine learning as well as artificial intelligence. So translating the use cases with the right tools. As I mentioned earlier, many applications can do the same thing, but that doesn't mean that you should use that one single application to perform all of your workloads. So when we talked about here, take, for example, here are some of the applications that we have within Amazon EMR. That might include Hive, Pig, Spark SQL, streaming, and so on. Some of these will fall under your batch category, also interactive, amongst other things. Now, one of the things that I would like to talk about in particular that we start off is the storage layer. So underneath over here, backing all of this, we have our storage. In this case, Amazon EMR, it works really well with Amazon S3 through what we call EMRFS. And this is what we're going to be talking about next, which is the storage that you should be using for your environment, as well as talking about best practices for it and what you should use, as well as optimizations and tunings that you can apply for your storage or using Amazon S3 for your storage. So first off, there are many storage layers that you can choose from. Take, for example, EMR over here, where you can choose between S3, Redshift, Kinesis, RDS, and so on. We're not going to be talking about all of these storage today, and we're primarily going to be concentrating on Amazon S3, since that is the bread and butter for many of the analytics services, which we'll show later on down some slides. So why Amazon S3 as your persistent data store? Here are some of the different benefits that Amazon S3 will provide. First off, S3, it is natively supported by all the big data frameworks like Spark, Hive, Presto, and others. And also a big important factor here is that it allows you to decouple your storage and compute. So there's no more need for you to run compute and nodes for your storage. So this means that if you need to scale your storage and you're using S3 for that, you no longer need to be thinking about adding nodes to your cluster. S3 is scalable automatically, so you don't have to worry about none of that. And it also allows you to run this transient versus long-running clusters. So take a transient cluster, which is a cluster that you run for a job, and it gets terminated once that job is done. If your data is being stored in S3, there's no need for you to keep that cluster around if you're not running a job. So again, you can have a very cost-effective and scalable environment for that. And one of the other things that comes with that is that there are multiple heterogeneous applications and services that can also use that same data. Take, for example, Redshift Spectrum or Glue, Athena. All of these are services that actually uses data directly from S3, which allows you to be also, maybe you're running a particular machine learning from an EMR cluster while you're doing your ad hoc queries from Athena elsewhere, all using that same data set. Also, S3 is used for 11 nines of durability, and you keep with that a very low cost for your infrastructure. Now, what about HDFS as well as data tiering? HDFS is still available in EMR if you choose to use. Some of the use cases for you to still use HDFS can be for your very frequently accessed data or your hot data. So if you have a use case such as that, you could, for example, store your data in HDFS, and those results, you can then move it over to S3 once the job is complete. Also, you can use your Amazon Glacier for cold data or storage archiving, and as well as the other different kind of data tiers for Amazon S3. So talking about decoupled storage and compute, that's the example that I was talking about earlier. Here in the middle, we have our compute, and take, for example, a service like Amazon EMR, Redshift Spectrum, and Athena. All of these can be using that same data set from S3 directly. While if you're needing to have a persistent Metastore, you can also today use your external Metastore in either RDS or actually use our newest feature for EMR, one of our newest feature, which is keeping your data catalog using Glue data catalog for your Metastore, which will be one of the points that we'll be talking about here shortly. What are some of the tips for S3 to make it optimized for you to run S3 as your data store? First, some of the considerations we have here is partitioning, compression, as well as file formats. So when you partition your data, you're actually reduce the amount of data that needs to be scanned. So that's going to not only improve the performance of your job, but if you're using something like Amazon Athena, where you pay for how much data gets read or how much data gets scanned, for a service like that, you're also going to optimize the cost for it. So this has a two-way streak here that not only you're optimizing the job itself, the performance, but you're also optimizing the cost for it. Also, you should avoid small files or large amount of small files on that same S3 location. So you should optimize your file sizes, which typically means you should keep them closer to the HDFS block size, which might be 128 megabytes. So fewer files matching the HDFS block size, that means that there will be fewer calls to S3, fewer listings, and better performance overall. Next, you should compress your data to also minimize the amount of bandwidth going from EC2 to S3. And that also, it's going to improve not only the performance, but for something like Athena, where you're paying for what you read, once again, optimizing the cost for it. And lastly, you should utilize a file format like Parquet or ORC, which can also improve the performance of your reads. So here are some quick examples of data partitioning where we can do an alter table, or you can do an MSCK repair table for a Hive compatible format. But these are just an example to outline how to partition that data. For file formats, in particular talking about columnar formats, we have Parquet and ORC. And that includes automatically compression or better compression for your data set. Also, it is columnar based, which means it is read optimized if you're having a particular column as part of your filtering. And it is also integrated with index and stats. For row formats, we have Avro, which is also good for compression. It is row-based optimized, and it is also integrated with indexes and stats. And last, we have a text format that includes CSV or your JSON file formats. But for a text format, it's usually going to be slow, not very, it may or may not have compression. But the good thing about it is that it's very easy to use and is very malleable and generic. So here's some quick 2 example queries that we ran to kind of list the difference performance from the 2. So here, both of these are actually data stored in S3. But here, if we do a select count for a CSV file format, we can see that the first example using text format, it took 36 seconds and 15.9 gigabytes of data was scanned. Now the same actual query, but run from your Parquet file format, it took only 5 seconds and only 4.9 gigabytes of data scanned. So here this kind of outlines the difference between using a columnar format versus something else like CSV or TSV and so on. And to wrap up some of our file considerations here is that for scanning, if you're actually looking for particular columns, you should maybe look into a columnar format like Parquet or RC. If you have read access that's based on a row format where you're utilizing just a portion of your rows, then something like Avro or a row optimized format might be good for that. And as far as write performance goes, usually it's going to depend on your use case, but text usually tends to be very slow. So talking about the external Hive Metastore, which I mentioned earlier, with EMR today, if you're trying to use an external Metastore, you have two options. One is to use an external RDS instance, and the other one is to use the data catalog, Glue data catalog feature. And with Glue data catalog, you have the search Metastore, and you can also keep your schema and version management, and you can utilize Glue's crawlers to be able to detect schema changes whenever something happens with your data. And also the other good thing about the Glue data catalog for your external Metastore is that it allows multiple services to share that exact same Metastore. And that includes services like Amazon Athena, as well as Redshift Spectrum and EMR and Glue itself. All of these services can share the exact same Metastore for your jobs. And to use Glue as your external Metastore is simply a check of a button through the AWS console if you're launching the cluster through it, or you could also just type in the parameter option for that if you're launching the cluster via the SDK or CLI. But here, the one thing that I would like to, as a side note, is that these EMR is just getting updated so quickly that just last week we actually announced, we released our newest EMR release, which includes Presto support for using Glue's data catalog. So here we have Hive and Spark, but just note that last week we also released Presto support for it. So to change a bit of pace, let's talk about cost optimization, and in particular about EMR and how you can optimize your cost and build a scalable environment. So one of the newer features with EMR is the instance fleet features, which allows for advanced spot provisioning of EC2 instances. I'm not sure how many of you are already experienced with using spot instances, but previously a lot of our customers had issues with it because sometimes it requires you to know what is the bid history, what's going to be the best bid that you can make on a particular spot, and so on. So by introducing the instance fleet feature, it pretty much takes care of all of that provisioning for you, where it's going to pick out of a list of availability zones something that it can make the best spot request for your cluster. Also, this takes us to back to our swim lane of jobs, to where now you got to make the decision of running a transient cluster versus a long-running cluster. So if we look back at our swim lane of jobs, we see that two perfect candidates for a long-running cluster would be a NoSQL or something like a real-time streaming application that needs to be running at all times. So for these, you can leverage a transient cluster and use spot instances for it in this case. While for these, you can use a long-running cluster and also have reserve instances, so on. But then we have our transient cluster use cases, which those are your batch reporting or your analytics that runs a few times in the day. For those, you can take advantage of using your spot instances and only pay for what you use. And to add to this, another newer feature that's been released for Amazon EC2 as well as EMR is the concept of you pay per second billing. So before, you had to launch an instance, and you usually pay for the entire hour once you launch an instance for EMR. But this is no longer the case, which now you pay literally for the minute that you're using an instance. So if you launch an instance, you can use for 2 minutes, and you're going to pay for just those 2 minutes, which brings us to our auto-scaling feature, which EMR has also automatically auto-scaling built into it, to where you can configure CloudWatch metrics to be able to scale out and scale in your cluster, or add and remove nodes based on particular metrics. That might be the amount of memory that the cluster is utilizing, the amount of containers you have running, and once again, all of this is you're only paying for what you use. And to wrap up over here with one of our final slides is the security and governance and auditing. And here are some of the different features that we have and the different services. Now, one thing to note about that is just last week, we actually also released a newer feature for EMR, 2 different security features, which one of them is a security feature that allows for Kerberos, native Kerberos support in EMR. So today you can just, with the click of a button and a configuration setting, you can Kerberize all the applications within EMR and be able to integrate that with something like Active Directory. And the other feature that we also release is storage-based permissions for EMRFS, which now you can have an OS user inside the EMR cluster, whenever that operating system gets logged in, or SSH, it's going to assume its own IAM roles and get the permissions of that particular IAM role. So you no longer have to have a cluster dedicated for different permissions. So you can have now EMRFS or S3 fine-grained permissions with it. So with that said, I'm going to hand off now to Ritesh, and he's going to be covering about Vanguard's migration story.
Bruno, thank you for that short introduction. Ritesh Shah here, work in Cloud Analytics Services team as a program manager. It's part of Chief Technology Office within Vanguard. Before I take you all through the Vanguard journey for migrating to EMR, I want a quick show of hands for 3 questions, right? First one, how many of you know Vanguard as a company? Okay, good. Second question, how many of you use Hadoop on-prem today? Okay. Third question and the last question, how many of you are either in process of migrating or considering migration to EMR? A lot of it, okay. So I'm gonna get the first question answered for people who don't know Vanguard. First thing first, Vanguard is one of the world's largest investment management company. Core purpose is to take a stand for all investors, treat them fairly, and give them the best chance for investment success. That's what Vanguard stands for. While I walk you through the Vanguard journey, we have 3 sections that we'll go through. First, we'll go through deconstructing on-premise Hadoop infrastructure. Second section would be deconstructing or demystifying EMR. And then third, what's next for Vanguard. Quick raise of hands also for how many of you have seen this kind of Hadoop cluster workload at your place, at your company, big, small, any size, right? This is a typical setup for a Hadoop cluster where you have different types of data stores running on-premise or off-premise, and data for it is brought into a Hadoop cluster, and then you have different kind of analytics done on Hadoop cluster using different components, right? You have a data analyst, you have a data engineer or a data wrangler, or you have a data scientist accessing this one Hadoop cluster where you have large volume of data. And you typically end up using components like Core Hadoop, Hive, Oozie, Scoop to bring that data in, Sentry. If you use Cloudera, you use that to secure your cluster from an authentication and authorization perspective. Many of your analysts and scientists use Impala through a Hadoop user experience interface. And then you may have enabled Spark, Python, and Tableau for your analysts and consumers of analytics. Next, why migrate from on-premise to AWS? Most of you may have run in one of these situations where your infrastructure for compute and storage is tightly coupled. Second, your cluster gets overutilized at peak hours and underutilized at non-peak hours. There is cross impact from different workloads. a data scientist running a experiment versus an analyst trying to just analyze sets of data. You may have cross impacts. Many a times, having one cluster, humongous one, gets you into a situation of not having a disaster recovery kind of environment if needed. And the last one on this section is you have dedicated teams to maintain this cluster day in, day out for upgrades, adding new hardware, software patches, etc. More reasons. Many a times, big enterprise companies run into long procurement cycles for procuring the hardware and attaching it to your Hadoop cluster. Long setup times to add that hardware. Complex upgrade coordination because it's a multi-tenant environment. You have to convince everybody to migrate to a newer version of Hadoop at the same time, which all leads to high total cost of ownership and difficult to charge back to line of business on what's the actual cost they are incurring for running a Hadoop cluster. Moving on to the second section, demystifying EMR workloads. Let's start with the first important thing that Vanguard did, right? Before moving to EMR, they set up a foundational requirements they wanted to achieve. Let's start with secure. When we wanted to move to EMR, we wanted our data to be secured in a way that data being moved to EMR would be encrypted in flight, and when it lands on S3, we wanted it encrypted. Second piece, we wanted a flexible workload where we could have our compute be customizable based on what workload it is being used for. Third one would be reduce the administration, so embrace managed services and managed way of working in EMR. All of that leading to lower total cost of ownership where you pay per usage. Bruno mentioned they have introduced per second billing. You can get to a lower total cost of ownership. It also we wanted full control where we wanted our infrastructure to be spun up or spun down as code and not a physical hardware that needs to be spun up or spun down. And last, we wanted a scalable compute and storage. When we meant scalable, we wanted to scale the storage irrespective of having to scale the compute hardware. Next one, we are going to start diving deeper into different workloads. Let's start with an ingestion workload for EMR. Here you would see different data stores, just like Hadoop, data flowing into EMR, and EMR being the single point through which the data would get written into S3, which would be our data lake where all the data resides. We utilized EMR S3 as a data lake. All the data was encrypted using KMS, and all the data was secured through IAM policies. We use step actions and step APIs to launch our Uzi workflows. We also used a lot of alternative mechanisms to bring data in. We used Snowball, we used Attunity, which is a change data capture tool, and we also use Scoop to ingest data. From a processing perspective, we use Hive or Spark or combination of both based on the needs. And we use CloudWatch in conjunction with Splunk to monitor all the ingestion processes that are happening. We also learned lessons along our journey. We quickly learned segregation of infrastructure and code is important. We need to keep our code for compute separate from the business logic. Lessons learned around instance type and cluster sizing that we would use. Each workload to bring data would require a different cluster sizing and instance type exercise. We decided to obfuscate all known PII data and segregate the data based on different business lines. Diving further deeper into conceptual diagram, this diagram shows 3 different compute mechanisms. First one is we spin up ephemeral EMR clusters for ingestion. We have FTP nodes, and then we have persistent FTP nodes. Let's start with an example where you would have a relational database. We ingest that data using EMR, scoop, and load it into S3. While doing that, we also build Hive tables on top of it and catalog it using Hive Metastore. Another workload where we need real-time or semi-real-time data, we use Attunity to replicate that data into Postgres SQL, and then we utilize the EMR cluster to process it and put it into S3 and build Hive tables on top of it. We also have FTP processes where we use data to be pulled in using ephemeral FTP nodes and then put it into S3 bucket. This FTP is secure FTP or SCP, so that data is encrypted in transit. And then we do have third-party vendors that ship data to Vanguard, and we have an internal team that takes that data and pushes it into S3 using persistent EC2 FTP nodes. Now moving on to the second section, a different workload. It's around analytics workload. Typically, you would have an EMR cluster that works with data in S3, and the consumers are data analysts, data wranglers, and data scientists. Typically, you would have a persistent EMR cluster that would auto-scale. You would use Hive, Presto as your query engines, and Spark and Python for distributed processing. We use Hue and Tableau as user interactive tools, Zeppelin and Jupyter-based notebooks that we are about to introduce for interactive and collaborative data exploration. All the authorization is done using Hive SQL Auth and IAM bucket policies on Amazon S3. Continuing the same theme, what did we learn? We quickly learned that data governance is a very important thing. We should have metadata lineage and other data governance capabilities enabled on the platform. Auditing, who ran what query, who accessed what data is very important. Instance type and cluster sizing for different workloads is important. And lastly, but most important, integration of all these user tools with processing engines. We learned a lot while establishing all that at Vanguard. Diving deeper, one level deep into a conceptual diagram, we would have query clusters that get spun up using Control-M. And these query clusters would interact with Hive Metastore for information about the tables and would utilize S3 for your data. We also enable Tableau integration using these query clusters so that it can be used for visualizations. The other workload that I talked about was around data science EMR clusters. These EMR clusters would typically run Spark, Python, and Zeppelin, and they would work with Hive, Presto, and S3 as the storage. And here are the 3 different actors, data analysts, data wranglers, and data scientists working with appropriate components of the EMR workload. Last section, what's next for Vanguard? Most important thing, real-time data ingestion, enhanced data processing pipelines, visualization and analytics use case, experimentation with AI and machine learning Those are the 4 areas Vanguard's going to start focusing on in future, and it's going to use plenty of other AWS services to move down this path. At this point, I'll give it back to Bruno.
All right, thank you very much, Ritesh. Thank you all. So at this moment, I would like to give you a moment for any questions or anything in particular you'd like to talk about. And feel free, I don't believe we have a microphone for you guys, but feel free to approach here if you have any questions, and we can talk about it. Thanks again, everyone, for coming. And once again, please remember to rate this in the mobile app.